Okay, thank you. All right, thank you, Mary Beth, and everyone for joining today. I will be giving a brief overview of the Maunakea Spectroscopic Explorer project. I have this lovely talk title given to me by our Director of Strategic Communications, Mary Beth Lachak, Chasing Rainbows, which is what we do with the MSE. Someday we will be taking spectra of spectroscopic surveys of millions of objects across the sky. And we're very much looking forward to planning this project over the next decade. I'm tell you a little bit about the design of the instrument and the plans for the scientific capabilities. I'm Jen Marshall. I'm the project scientist of the Maunakea Spectroscopic Explorer project, and I'm a professor at Texas A&M University. All right, so just to start with a little bit of background, the MSE project comes out of the Canada-France-Hawaii telescope. I like to say it's a reimagination of this excellent facility on the summit of Mauna Kea that has a more than 40-year history of very strong scientific productivity and also public outreach on the Big Island. The MSE project very much plans to continue on in that same vein and build on the strong reputation of CFHT. And so as a result, we have a goal of minimizing the impact both in a structural sense and in a cultural sense to the site of the telescope. And we are planning to sorry, my husband just walked into the room and that was very distracting. We are planning to minimize the impact, as I said, of the facility. And as you can see here, once the construction is complete, we will end up with a very similar looking facility, and that is very much by design. The plans that we have made come out of an exercise that the project went through a few years ago, culminating in a conceptual design review in 2018. You're looking at a fly-through view of that conceptual design. This video is put together by Greg Green, one of our the CFHT engineers that contributed to the MSE conceptual design. And you can see that this is a real conceptual design of a telescope. There's a big telescope crammed inside of that almost the same size dome as what is in CFHT. And I will stop playing the video now and talk to you in show you a static view of the telescope so we can talk about what you're looking at. So this is an overview of that conceptual design. As I said, the telescope is a large telescope inside that dome. It's 11.25 meters in diameter. It's a segmented mirror design with the prime focus of that primary mirror feeds a fiber positioner at the top end, at the prime focus of the telescope that has a 1.5 square degree field of view. In that field of view, there are positioned 4,332 fiber positioners on a robotic fiber positioner unit. 3/4 of those fibers feed low to moderate resolution spectrographs. So those are spectrographs that operate at resolutions of 3,000 or 6,000 in a wavelength regime from the ultraviolet all the way out into the H band in the near infrared. And 1/4 of the fibers feed high resolution spectrographs that have spectral resolutions of 40,000 in 3 very narrow optical wavelength windows in the blue, green, and red parts of the optical spectrum. And I like to say when I show this slide that what you do not see here is anything else. So we are a completely dedicated survey facility. We will only take spectroscopic observations of large samples of stars and galaxies. MSE has been put together by our participant institutions that you can see here. So in addition to the current partners of the CFHT telescope, Canada, France, and Hawaii, we also are joined by Australia, India, and China, as well as more recently, Texas A&M University, my institution, and Kyunghee University in South Korea, as well as we have received expressions of interest of joining in the near future from institutions in the UK, as well as the US National Science Foundation's Noir Lab, the institution formerly known as NOAA. And with this group, I think we are, it's an excellent group of collaborators to execute a project such as MSE. So I'll just spend a few minutes describing in a little more detail the conceptual design of the instrumentation, and then I'll spend a few minutes talking about some of the very exciting science projects that we'll be able to do. So as I said, at the top end of the telescope, there's a fiber positioner robot that you can see some conceptual design drawings of here. The large multi-red and blue colored hexagon in the middle of the slide here shows the fiber layout of the fibers that feed to the LMR spectrographs and the HR high resolution spectrographs. So the red dots correspond to LMR spectral fibers, and the blue dots correspond to high resolution fibers. And as I said, the field of view there is 1.5 degrees in area. The design of the fiber positioner robot was done by our collaborators in Australia, who have, of course, a very long and strong history of excellence in developing these things. So we're very much building on their expertise. Similarly, our collaborators in France at CRAL, and also now at Marseille, at LAM, have designed the conceptual design for the LMR spectrographs. There are 6 of these units that accept those 3/4 of the fibers that I mentioned from the focal plane. And you can see the conceptual design here. They're split into 3 arms in the optical and then 1 arm in the infrared. So there's a red, blue, and a green channel. I should say blue, green, and red channel, and a near infrared channel. And they, as I said, operate over the entire optical window and out into the near infrared at 2 resolution settings, both resolution of 3000 and resolution of 6000. And then the high resolution spectrographs live down in the basement of the telescope facility so that they can be more stable, spectroscopically and resolution-wise stable. And the 1/4 of the fibers go to the high resolution spectrographs. There's 2 of them. And they operate at a very high resolution of 40,000 in these blue, green, and red arms as well. If you would like to find out more details about the MSE conceptual design, you can go to our website and you'll find nice tables that look like this that have all of the details and all the numbers of anything you might want to know about the conceptual design. So as I said, the conceptual design review happened in 2018, and before that time and then since that time, we have continued to advance the scientific planning for the facility as well. And in particular, we do that by organizing our very large science team. We have more than 400 scientists involved in the scientific planning of the project. We organize those 400 scientists into 8 science working groups that you can see here, and you can also see the names of the 2 co-leads for each one of the science working groups. So you can see, and you can maybe imagine that a facility like MSE, a next generation, highly capable, highly adaptable spectroscopic survey with lots of fibers on it, can do a lot of different kinds of science, and that's reflected in our science working groups. So everything from nearby stars and planets to high resolution observations of those same stars, studying the chemical abundances of the stellar atmospheres. We can do that in the near field, we can do that in the midfield, and we can go out into the high redshift universe and study galaxy formation and evolution and AGNs at the centers of those galaxies. We'll also be able to study more astrophysical subjects such as tests of dark matter and cosmology, our cosmology case is particularly notable, I think. And we'll also be, of course, be able, especially because we are a completely dedicated survey facility, we will be able to do a lot of projects that are related to time domain astronomy. So I will not have time to talk in great detail about all of those topics today, but I'd be happy to talk to anyone who's interested in talking to me or in our talking to the co-leads of our science working groups. We can put you in contact with them. There's a lot of really exciting stuff to talk about. I guess I will start that conversation by referring you to the document that was put together by our science team. It was published on the archive last year. 2 years ago now. And then we call it the detailed science case for the Maunakea Spectroscopic Explorer. So that document has 300 pages of certainly not all of the science that MSE will be able to do. It's not even close to trying to discuss or overview all of the science that MSE will do, but it gives a compelling argument. The goal is to make a compelling argument scientifically for why a facility like MSE needs to exist from a scientific perspective. And so what we've done is picked out some of the most compelling arguments, again, scientifically, for building a major facility like MSE. And so I've picked out some of my favorites here on this slide, but there's many more in the document. And so I'll talk briefly about a couple of these. So the reason that I got very excited about the MSE project before I had joined it is really our capabilities of studying vast numbers of stars, stellar atmospheres, and understanding the chemical composition of the stars of an unprecedented number of a sample of stars, and probably an unprecedented sample of elements when we get done with it. And in particular, I'm particularly interested in using the MSE data and our survey capabilities to understand where the relative chemical abundances of all of the elements in the stars, but in particular the origin of the elements, the formation processes that must have gone on in the early and recent universe to produce all of those elements inside of in astrophysical processes. And in more detail, I'm very interested in answering the question of where the R process elements were formed in the universe. We've seen that in one example, thanks to the LIGO project 3 years ago. We watched a neutron star merger happening and producing our process elements, and I was somewhat consistent with what we think is how our process elements are formed. So our process elements are the orange colored elements on this periodic table here, but that was the first observational evidence of our process element production. And so with MSE, we should be able to, maybe not in real time, maybe in real time if LIGO finds more our process elements for us, but we'll be able to assemble large samples of fossil records of our process element production in the observations that MSE will be able to make. We'll also be able to study very detailed, we'll be able to answer very detailed questions about the composition of exoplanets. So if you look in the top middle figure here, you can see that this very clever science case to use observations of white dwarf stars and figure out from their detailed spectra what planets must have fallen onto the surface of the white dwarfs, polluted them, and it's a clever way of learning a lot about what exoplanets were made of in a unique way. I think that MSE, because of our large sample sizes, will be able to make great strides in. As I said, we can answer questions about astrophysical questions like the nature of dark matter, and on the top right, you can see that MSE will be able to do observations of ultra-faint dwarf galaxies, very large samples of them, and more stars in each one of the dwarf galaxies than is currently possible with today's telescopes. This is a field I've worked in the past, and it's just very exciting to think about it expanding doubling the number of galaxies studied and being able to understand in much more detail the results that reflect on the nature of dark matter. We'll also be able to study, as I said, extragalactic sources. So on the bottom row, I have 3 cases from our extragalactic scientists. On the left, I highlight the capabilities of MSE's observations in terms of constructing extragalactic surveys. MSE will be able to construct one of the deepest and largest area surveys of galaxies that is possible. And so we'll be able to do a lot of really interesting and very different things with that, with that survey. We'll be able to do things like study quasar absorption spectroscopy. So do projects like that that were revolutionary and done by the Sloan Digital Sky Survey, but do it for orders of magnitude more targets and fainter targets. So we're very excited about that kind of science. And as I mentioned previously, the cosmology science case for MSE, I think, is really excellent and exciting. So we'll be able to use, again, samples of surveys of tens of thousands of degrees of the sky and millions of galaxies at a range of redshifts, mostly a high redshift, to answer questions about the non-Gaussianity in the early universe, putting constraints on this sigma FNL parameter that you can see in the figure. But also, and I think this is just very cool, we'll be able to measure not only the combined neutrino mass, but also put constraints on the hierarchy of the neutrino mass. So again, let me refer you to this document that summarizes all of these and many more cases. Okay, so each one of those science cases that we talk about is in a project that can be done in all of those examples I just gave, can be done primarily using MSE observations. But we also really like to think about MSE as a cornerstone in the future landscape of observational facilities. And so this figure is kind of highlighting that aspect of MSE. So we can think about this in many different ways. So MSE has obviously strong synergies between following the Rubin Observatory, following up imaging done by Rubin, and maybe taking those images, getting spectra of interesting things, and then passing on a subset of those, of the most interesting stars or galaxies found in the Rubin imaging to the 30-meter class telescopes for even more detailed spectroscopic follow-up, as one example. MSE also has obvious synergies between our optical and infrared wavelengths to facilities at longer and shorter wavelengths. So facilities like ALMA and SKA, and space-based facilities that are soon to be operational. And so again, we like to not only think of MSE as an excellent standalone spectroscopic facility, but also very synergistic with these other facilities as well. So I will just briefly mention the timeline to science operations. So we are, I hope you're excited about this project. I certainly am. It's not going to happen tomorrow. We have a lot of work still to do, a lot of planning and engineering design work, and then some construction. But the current plan, the current schedule says that we should be able to begin science commissioning in 2030. Actually, it says 2031 as of now. I didn't update this slide. And we are ready to, what we're doing right now in the project office is making sure that everything is ready to go to begin the preliminary design phase, which could in principle start next year. Once we start that, we'll have a 2-year-long preliminary design phase, and then we'll be able to begin construction. And as you can see, the timeline here lays out the plans leading up to science commissioning, again, around 2030. So if you are watching this and you are not a member of the science team and you like what you hear, I very much would welcome you to join us. It's free to join, and all you need to do is send me an email, and we would love to have you and hear more about your scientific interests in the project, and have you help us build the science case for MSE. Please do. And I will say thank you for your attention and leave up our put up our acknowledgements here before, yes, moving on to another nice animation that was put together by Greg Green this past year. I can take questions from the audience.